What we're going to be looking at now is the MRS Notebook 2. So if you're in the IFU session, you're going to double-click MRS Notebook 2, and that should pop up this thing here. And what this is going to be doing is discussing how to process large quantities of data all in one go. So when we're actually looking at most of the observations that we're likely to get in cycle 1, then we're not going to be processing a single exposure. If you're redoing things yourself, you're most likely to have multiple grating settings, multiple dither patterns, perhaps even a mosaic. And so you want to be able to process that all as efficiently as possible, even if you're working just with simulated ground test data now, so something coming out of the MIRI sim simulator, for instance. You want to be able to churn through all those files as quickly as you can. And so what this notebook does is it shows you how to implement parallel processing using multiple CPUs in a notebook environment with application to processing MIRI MRS data. And what we're going to do is we're going to follow much the same setup as what James was just doing. We're going to show you how to import the various Python pieces that you need for the pipeline, how to set your reference files properly, how to define your input directories for the data itself. We're going to show you an efficient means of running all the data through the Detector 1, Spec 2, and Spec 3 pipelines. I'm going to show you 3 different ways to configure the cube building stage of Spec 3 so that you can produce slightly different data cubes out the other end to take a look at, depending on what your science needs are. And finally, we'll look at the outputs and compare the spectrum that we got out of the pipeline at the end to the spectrum that we sent into the simulation tool at the beginning as a sanity check to check that you get out what you put in when you're working with perfectly well understood simulated data, as a check that the pipeline's doing what we expect it to. So this is what we're going to be working with. We're going to be simulating a point source observation. In this case, we're taking a point source in the middle of the field with an astrophysically realistic spectrum. In this case, taken from the active galaxy NGC 5728. We're going to be using all 3 grating settings, so 5 through 28 microns, and a recommended 4-point dither pattern. There's a lot of caveats I've got in here about working with simulated data. The data we're using are produced by MIRI Sim, which is a simulation tool provided by the MIRI instrument design team. There's a number of gotchas about using this tool at the moment, though, and known issues that can complicate trying to run data through the pipeline. I list a bunch of them here. I won't talk about them all explicitly now, but I'll allude to them later, and you're of course welcome to read through this on your own time later. If you're interested in working with simulated data as well, it'll tell you a couple things to watch out for and how to work around them. So the first thing we're going to need to do, and now if you want to start clicking along with me, this is the first cell that you'll want to shift enter on in order to actually run it, is we're going to need to set our CRDS context. What CRDS is, that's the Calibration Reference Data System. This is the version control system for all of the reference files that are used by the pipeline. Here we move down to importing various Python packages. There's lots of convenience functions that I'm going to be defining here that are intended to work, really allowing this to be a template notebook that you can use when processing your own data later, to use multiprocessing to take advantage of the multiple cores in most machines nowadays. And what all of these sort of boilerplate things do is they set up that multiprocessing framework so that we can use it effectively. So we've imported some basic multiprocessing packages. We're setting up a few things with how the pipeline needs to run in multiprocessing mode and where it sends the log files, etc. This cell here defines how many cells we're going to be using. In this case, we said usage equals none. So by default, if you run this notebook, you're not going to be using CPUs. We don't want to tie up all the CPUs on your machine unless you explicitly want us to. If you wanted to turn that on, you just change this usage none to usage all or half or some fraction of your cores. And then down here, the cell just tells you how many it's going to be using in this particular run. In this case, just 1 CPU. A few other boilerplate imports. We're going to import some general utilities for interacting with files. For those of you who are familiar with notebooks, this is all the standard things you're used to. System utilities, AstroPy, file inputs, plotting functions, etc. Here's where we're going to do our first JWST import, and we're going to check that it's version 1.1.0, mostly because a few other things later on in this notebook depend on that particular version, so it knows where in the pipeline to grab different packages from. This is something that will, of course, evolve over time in later versions of this notebook as well. And this step is where we import the actual JWST pipeline, so Detector 1, Spec 2, and Spec 3 pipelines. You can ignore all of these warnings coming out here. Those are mostly about issues with PySynfo, which are irrelevant for purposes of what we're doing today. And finally, we can move on to defining the data directories. So if you're interested in getting the data I'm working with today to download and work with yourself at home, here's a link to a box folder here that you can get them from. It's quite large, so you might want to set it to download, then go get a coffee or something while you wait for it to finish. If you want to run it on your own machine, then you're going to want to set this path here to point to where you downloaded the data from Box. Because it can take quite a while to actually process the data and download it, then for today, when everybody's working in this webinar environment, we're actually going to be all pulling from the same local location on the webinar server. So this is the cache directory that we're going to be pulling actually both the input files produced by MIRI from, and also staged versions of all of the output files as well, simply because they take a long time to run. We're going to specify some working directories that we want our data products to go into. Personally, I like having my files from different parts of the pipeline spat out into different directories so I can keep things clean. So this now created, as you'll see in the left window, the stage 1, 2, and 3 directories. Those are going to be the outputs from the stage 1, stage 2, and stage 3 pipelines, nicely separated off so that you can find what you're looking for later. And finally, we'll define this reprocessing flag. This is right now set to false. This tells the notebook whether or not it wants to actually run the pipeline or just skip the lengthy steps and copy the results out of cache. For today's purposes, we're going to be running it with false, so we can copy results out of cache instead of running them in real time. After this session ends, you're welcome to rerun this notebook with it set to true, and then it will actually run all of the pipeline steps for you, or you can, of course, do this on your own machine at home later as well. And finally, a multi-threading function that is another convenience function that allows us to interface with the multi-thread capabilities that we've built into the Jupyter Notebook environment. So with that preamble out of the way, now we're actually ready to actually run the pipeline. So if you're interested in, say, using this notebook for your own purposes to process your own simulated data, your own flight data, here's where you're going to start actually looking at making any modifications you want to make to the pipeline. Up above, you'd really just be modifying things like number of CPUs, data input directory, etc. So the first thing that we'll do in order to run Detector 1, we want to run it fairly efficiently. We'll just define a function that wraps an instance of the Detector 1 pipeline. So it's calling this thing that we imported from the JWST package earlier. And here's where we'll make any modifications that we want to make to that pipeline. In this particular case, I'm going to set the output directory to this stage 1 directory here because we want to separate it off so we can keep our different products in clean directory structures. I'm going to disable the reference pixel subtraction step. This is because this is one of those MIRI sim gotchas I alluded to earlier, where the MIRI simulator doesn't process reference pixels in the same way as what flight data will be doing, so the flight algorithm pipeline doesn't do a nice job working with simulated data here. The workaround is just to turn off the pipeline reference pixel subtraction step when you're dealing with simulated data, and here's how you do it. Next cell is where we look for all of the input files. In this particular case, it finds all 24 of those files that we expected. So this is 4 dither patterns times 3 grating settings times 2 detectors for each gives you 24 input files, and it's found all of those. In this next cell, this is where we actually say, call the pipeline, run the pipeline on those files. So if this redo long flag is true, we're redoing these long pipeline steps, then it's going to send this run detector 1 function, this list of files to input, and because of the multi-processing wrapper we've got, then it'll actually spawn those off to lots of different CPUs to process them all efficiently, as opposed to just doing one after the other. For today, though, then, it's actually just copying those files out of the cache directory. And the results that we're getting out of it are these so-called rate.fits files. These are the uncalibrated slopes that are in things like counts per second units. And with that, we're done with Detector 1, and we can move on to the Spec 2 part of the pipeline. Here we'll do pretty much exactly the same thing, and I'll just shift enter through the rest of the cells in this section so that those can work on running while I'm talking about what they're doing. Here's where we've defined the Spec2 pipeline and instantiation of that, and we make any modifications we wish to make to how that pipeline runs, turning steps on and off, overriding various different files if we want to, etc. And the only changes we're going to be making in this case is we're going to turn off background subtraction. The reason why we're doing this in Spec2 is largely because for point sources right now, background subtraction is really being handled in the extract1D phase. It's using this annular region to define a background when you're extracting a spectrum. There's two places in the pipeline where we might be able to do background subtraction that affects cubes in the end. One is in Spec2, which will be a pixel-by-pixel background subtraction, which is really a fallback option if we can't do something that's better from a signal-to-noise perspective. And a different step in Spec3, the master background subtraction, where we can do a model-based subtraction instead. Those are both still somewhat in works at the moment, and they're not really necessary for the demonstration today, so we're turning those off for now. Similarly, we're turning off the stray light step, largely just because the simulator doesn't include a stray light component, so it's really not necessary to have this in the pipeline that we're running today. After we've done that, we look for the input files. The inputs you want to send into the Spec2 pipeline are these rate.fits files that came out of the Detector 1 pipeline. It found 24 of them, as we expected. We need to make a little bit of a hack to these files to deal with the fact that simulated data is missing a number of the keywords that we'd really have for flight data. In this particular case, when you designed your APT files, then you had to indicate for each source you were looking at, is this an extended source or a point source, or is it unknown? And that provides guidance to the pipeline as to how it should process it through the later stages. It can also try and figure out what it is, even if you said unknown. If you said it's a point source dither pattern you want to use, it'll assume it's pretty much a point source then, and treat it as such for extraction. MIRI though doesn't have any of those keywords at all, so it just defaults to saying it's an extended source. In our case, we know we're processing a point source. That's what we actually want to deal with. So we're just overriding the appropriate header keywords here to tell it, no, this is a point source, please process it as such. And there might be cleaner ways of doing this later, but for now at least this cell will allow you to overwrite that as a point source. And here's where we actually run that step, much as we did in Detector 1. If this redo long flag is true, it would pass the function run spec2 along with our list of rate files that we want to run it on into this multiprocessing function so it can spawn it off to lots of CPUs. But for today, it's just copying it out of the cache directory. So now we've got calibrated data. We've got individual exposures that are radiometrically calibrated. They're the cal.fits files, and we want to run them through the Spec3 pipeline, which is where we actually start putting together lots of different files, all into big cubes. The first way we're going to try doing this is the default way that the pipeline does it. So this will be the data that you get out of MAST, as now these kinds of 12 per band cubes. What this means is, as you remember from earlier, then the MRS is split into 4 channels, each of which has 3 bands. That gives you a total of 12 bands from 1A all the way up through 4C across the wavelength range. And the default pipeline is going to give you a summary cube for each one of those bands individually. So you'll have a channel 1A cube that combines all your dithers, a channel 1B cube that combines all your dithers, etc. So you'll have 12 of those. And that's what this way of running the pipeline is going to do for you. We're going to define more useful functions. The first one, a way to write an association file. James mentioned this earlier. The association files are files where you list what should be combined together when you're running the Spec3 part of the pipeline. What are all of the files that I should be including in my list? If you're working with flight data, you won't need to worry about that so much because you'll get these association files from MAST. But if you're working with simulated data, you'll have to produce them yourself, and so there's a number of tools in here to allow you to do that. We're also going to split those files out a little bit. I'll shift enter through the next couple of lines just so you can see what it's going to do. What we did is we've actually sorted all of our input files by band, and we've created association files for each of these 6 blocks. So we've got an association file for channel 12A, an association file for 12B. That's not strictly necessary, but by doing so, we've got 6 association files, and we can then send each of these cube building instances of different processors of their own. So this allows us to do multiprocessing more efficiently than if we just had a single long association file. This cell here is where we define the Spec 3 pipeline, much like we did for Detector 1 and Spec 2. We import an instance of the pipeline. There's a little bit different sort of formatting here to make sure that it pulls in a most recent version of the default settings for that pipeline properly. And we can make any modifications that we want to it here. Here I'm listing the individual steps in Spec 3, and I've got all of them on except for master background in this case. Much the same reasons why we skipped this in Spec 2. That's because for point sources right now, we're doing background subtraction at the spectral extraction stage, and we don't actually need to do it at this master background step instead. This is something that's going to be evolving a lot over the course of the next few months, and as we get early flight data during commissioning. So we'll be providing more guidance on this as we get forward to actually looking at having cycle 1 data in hand. And this next cell is where we actually run that pipeline. It calls this multiprocessing function to spawn off lots of calls to our run Spec 3 function that we just wrote here, and runs it on this list of association files. Except, of course, for today, it just copies it out of cache. So we've now actually run the pipeline, if we were running the pipeline. But if you were running this at home and had it reprocessing, you would have finished running the pipeline now. You would have a lot of cubes, and we could look at them and see what they look like. But before we do, I'd like to try running the pipeline 2 other quick ways, just to give us some comparisons we can look at and see how the data products differ between these different ways you can try running it. The next way you can think of to run the Spec 3 pipeline is if you say, you know what, I don't want to work with 12 cubes just to cover the MIRI wavelength range. I want to have it be chunked up into broader segments to make it easier to work with. And that's entirely possible to do. You can make what are called per-channel cubes instead. So instead of having a single cube per band, you can have one for an entire channel spanning 3 bands. So now you'd have a channel 1 cube, a channel 2, a channel 3, and a channel 4. So you've got a quarter of the wavelength range in a single cube instead of just a 1/12 of the wavelength range. And we can do that in very much the same way as how we've made the 12 cubes earlier. First, we'll make an association file that lists all of the different bands together. So we're going to find all 24 of those input files and put them into a single association file. Now it's produced this thing, l3asn.json. Again, we could have run our 12-band cube on that same association file, but it wouldn't have allowed us to do any multiprocessing. And now we'll define a new version of this runSpec3 function. We'll call it runSpec3_channel if you want. And we're going to set that up in much the same way. We're going to make any changes that we want to make for the individual pipeline steps. Here I've turned a few more things on and off just for illustrative purposes. It doesn't really matter for the demo today. And I've given you a few more of the options that are available when you're working with the final stage cubes. Not all of these are things that you'll actually want to change, but they're just given here as a list of things that you could change if you wanted to. The way that you would ordinarily make a per-channel cube is you'd say this cube_build.output_type equals channel. And if you said that, then it would run and produce per-channel cubes after you've finished running cube building. You can change some other things as well if you're interested. You can change the weighting function that's being used to build the cubes. At the moment, the default is a exponential modified Shepherd interpolation algorithm, which is how you go from the point cloud of detector data to rectified cube data. We're in the middle of developing a number of other algorithms as well. We're hoping to have a 3D drizzle type algorithm in place sometime in the next few months as well. You can change the coordinate system in use for your cubes if you want as well. By default, they're aligned such that you've got north up and east left in your cubes. But if you want to change that so that it's aligned with the physical axes of the IFU on the sky instead, you're welcome to do so. The world coordinates are going to be perfectly accurate in both cases. You can change the scale of the output cube as well. You can think of this as the traditional drizzle parameters, what your output pixel scale is you want to do, but this is just for the 3 dimensions. There's a lot of things that you can change if you're interested in doing so. Here's where we actually rerun that step. Ordinarily it would run it. In this case, it just copies it out of the cache. The third way we can try running Spec 3, looking at a slightly different kind of cube, is if you say, that for your science, what you really want is you just want, give me the entire wavelength range, all in one cube. Give me 5 through 28 microns, all in the same data cube that you can scan through from one end to the other. We really don't recommend doing that for a couple different reasons. First, that now these cubes are huge. They're a gigabyte or so in size, even when you're working with just a single 4-point dither, let alone if you're looking at a mosaic. And they take a long time to build. The more important reason, though, is for sampling purposes, what you want to do at 5 microns and what you want to do at 28 microns are really very different. So if you can only choose a single fixed pixel scale, for instance, then you've either got to dramatically undersample your point spread function at 5 microns or dramatically oversample it at 28 microns. And that can give all sorts of weird artifacts in the cube that are non-realistic, and it's just a matter of the fact that you're choosing non-ideal cube building parameters. But if you decide that you don't worry about that and you just want to give something to view the entire spectrum, see what it looks like in one go, it's entirely possible to do so. These what we call uber cubes. We'll proceed much the same as before. We will define a version of the Spec3 pipeline, and we'll just make this call here to output type equals multi. In that case, what it means is just combine together everything you're giving in the association file into a single output file, and the pipeline is perfectly capable of handling that. If we then run that, it would ordinarily run here, and we would go have dinner or something for a while and wait about 6 hours for it to finish. Okay, no, it's not fair. Wait about 3.5 hours for it to finish processing this one cube, and then come back and look at it. For right now, though, it took a couple seconds just to copy it out of cache. Now what we want to do is actually look at what these output cubes look like. How do they compare to one another? How do they compare to the input spectra that we sent in, etc.? So what we're going to do is we're going to read in these channel 1A cube, the channel 1, all of channel 1 cube, and this all cube going from 5 through 28 microns, and compare them spatially and make a plot. So here's what it looks like if you were to take a slice at a given wavelength through each of these cubes. Just look at one plane of it so you can see the spatial structure. For the channel 1A and channel 1 cubes, you're seeing an image of the point source that we were looking at, and they look pretty much identical to one another. And the reason why is because by default the pipeline uses the same spatial sampling settings for the channel 1A cube versus for the all of channel 1 cube. Spatial sampling settings change between channels, not between bands. So these are fundamentally identical to each other. It's just that the channel 1 cube has a longer dimension in the wavelength axis than the channel 1A cube. The all cube looks quite different though. The data itself is still the same, but now it's actually embedded in a larger field of view. So it runs out, say, to 90 pixels on the x-axis as opposed to about 50 pixels. The reason why is, as I mentioned in the PowerPoint presentation earlier, then we've got effectively a stack of the different fields of view in a pyramid, if you will. If we're building all the data into a cube, you have to have your cube that's big enough to fit in the channel 4 field of view as well. So channel 1 will just be a sub-piece of that field of view that you're seeing here, and that's the main difference between the spatial view of these. We can look at them spectrally as well, so if we want to now plot a spectrum of all of them, then here's what we get. I'm now reading it in from the X1D product produced by the pipeline that's doing the aperture photometry with a PSF loss correction in each of these cubes. You can see here's the channel 1A cube, the spectrum of the sources, this teeny tiny little piece from 5 to 6 microns here. It's a 1/12 of the MIRI wavelength range. It just looks a little misleading because this is a linear plot. If I plotted it in logarithmic units, it would be a bit more obviously a 1/12 of the available wavelength range. The channel cube is longer, of course. It goes all the way out through the entire channel 1 wavelength range out to about 8 microns or so. And the Uber cube, as expected, goes all the way out through 28 microns, showing all of the data in between. So the final thing that we're interested in looking at, though, is, this is nice, but is it actually right? Does it look like the known answer that we sent into the simulation to begin with? So the next thing we're going to do is we're going to read in the actual input simulation, input spectrum that we sent into the MIRISIM tool when we made the simulated data that we've been processing through the pipeline. We're going to loop over all of the per-band spectra, the 12 per-band spectra produced by the pipeline for each of these cubes, and we're going to compare them to one another and see how good they look. And here's the result that you get. The black line here is the input spectrum that we used in MIRISIM to simulate our source, and the red line is the result that we get out through the other end of the pipeline, which is a nice illustration of the fact that the pipeline is more or less behaving exactly as intended, and it's giving a good match to the data all the way from 5 through about 18 microns. What's going on in channel 4 is actually not a problem with the pipeline, it's a problem with the simulator. This is another one of those gotchas I had in my list up above at the beginning of the notebook, where at the moment the simulator doesn't use the right photometric calibration for channel 4, so the pipeline cannot give the right answer because it's being given the wrong inputs. And this is something that should behave much better in flight, and we'll of course design the photometric calibrations to work appropriately with the actual on-sky data that we get. There's another little thing that's hidden a little bit in the math here. There was a kludge that I put in up here where I multiplied all of the output fluxes by 10% in order to make them line up with expectations. This is actually another simulator issue where the point spread function isn't quite what it's meant to be, so the PSF losses aren't what the aperture corrections are designed around for flight data. So it's just another illustration of how when you're working with simulated data, it's good to be aware of what the limitations are and work with those as necessary in order to make sure that you can understand the outputs properly.